Hello everyone. In this video, we will talk about covariance and correlation between two random variables.
Covariance is a measure of the strength of a linear relationship between two variables that are not independent. So let's say we have a random variable x and a random variable y. Again, as in previous example, x could be the washer thickness, y the diameter, and we want to see if there is a relationship between them. If x increase, does y increase, or the opposite, or they are not related. So a measure of this linear relationship and the strength of it is a covariance. And basically the covariance of x and y, it's the mean of the difference between every possible value of x minus the mean of x time every possible value of y minus the mean of y. And let's first visualize it. Then we will come back to this equation and how do we convert it to this simple equation. So let's look at this plot. Before even we discuss these plots, just by looking at this equation, if the covariance came large, that means there is a strong relationship. If the covariance came close to zero, that means there is no relationship between them. But let's see if these plots can help us see how we determine the linear relationship between random variable x and y. So if I ask you, looking at these three plots here, the horizontal represent all possible value for the random variable x, and the vertical all possible value for the random variable y. Now when we look at the first plot here, if I look at every data point here is representing, let's say we have a population here and there is x1 y1 x2 y2 xn yn. So these are data point in this population. It could be width and length, and then I plotted every possible bivariate points, and these are the points here. Now if I look at this graph, I can clearly see some linear relationship and it's positive. So if I plot like a line here, as x increase, y increase. If I look here, there is a linear relationship, but it's inverse linear relationship. That means when x gets smaller and smaller, y get larger and larger and larger. And here, when x get more positive and more positive, y get more negative and more negative. So the first two here, this one and this one, there is a linear relationship. The closer these blue points to the line, the stronger the relationship. Now if I look at this plot here, the third one, definitely there is no relationship between them. Because look here, at this x value here, at that x value I have a point of different value of y, another point of different value of y, another point of different value of y, another point of different value of y. I won't be able to tell if I know x what y will be. Same thing here. If I look at this line here, at this value of y, I have this point, this point, this point, this, and this, and this. So this point has different values of x. So there is no covariance, no linear relationship between them. Okay, so how we express it mathematically? To express it mathematically, let's look at this expression. For all points in this quadrature, x minus mu x, for this one, x can go as negative as this point for this, and as positive for this data point here. And the mean mu x in the middle. So for this quadrature, all points here, they have positive x. If I subtract from this point the average, which is here, this will always come positive, this quantity. Same thing for the y variable. The y variable range from here to here, and the mean of y is this line. So all points here again in the first quarter have positive y, or y larger than the mean, which is here. So that's difference again will be positive. and positive quantity times positive quantity will be larger than 0. Now let's look at this quarter. All x points here is less than the mean here. So x minus the mean, x here, any point here, minus this mean will give you a negative quantity. Same thing y. If you look at all these points, here, 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 these y's less than the mean of y. So y minus the mean will also give you a negative quantity. So now a negative quantity times a negative quantity, you get a positive quantity. So all these data point here will give you a positive quantity. All these data point here will give you a positive quantity. So positive times positive, you get a positive numbers, and then you take the mean of all these values, and the mean of positive value, you get a positive values. The only exception is data point in this quarter, which is in this has 2 points, this has maybe 3 points. Here in this quarter, x minus mu x will give you positive because x is larger than the mean here. But y minus mu y will give you negative because the y for this point is here, which is less than the mean of y. So you get negative. So you get positive times negative, you get less than 0 value. And the same thing here. You get less than 0. So of all these points, you have a lot of points that will result in positive quantity and few points in negative. So when you find the mean of many positive quantities and few negative quantity, the mean will become very positive. And if all data point around here, then you will have nothing in the negative, nothing in the negative, and everything would be positive, and that show you a strong covariance between x and y. And we can use the same analogy for this plot. In this case, you have a lot of data point that will give you negative quantity. A lot of data point in this quarter will give you negative quantity. So in this population, you have a lot of negative. When you do the multiplication here and here, you will end up with many negative values, many negative values, few positive value. Those are the few positive. So a lot of negatives, few positive, a lot of negative. If you find the mean of these, you're going to get a large negative value. So it could be minus 10, minus 15. So that shows you how strong inverse relationship between the random variable x and y. But in this case, now this will give you positive values, this will give you positive values. This data will give you negative when you do the multiplication, and this will give you negative value. So you will have almost the same number of positive and negative, and when you take the average of these quantities, you will end up with 0 or close to 0. And they'll tell you there is no relationship between the random variable x and y. And that's basically what's covariance. I can say it in a different way. I will create a new random variable z, which is x minus mu x times y minus mu y. Then the mean of z is the covariance, is this. So let's find what is the mean of z to show you that this is exactly the same as this. So let's continue. If I do here multiplication, so that will be z equal xy minus mu x y minus mu y x plus mu x mu y. So I just multiply this and I got this. Now if I want to find the mean of z, which is the covariance here, that will be mu xy minus. Mu x is a constant. The mean of the random variable y is mu y minus. Mu y is a constant. The mean of x is mu x. Plus this is a constant, and the mean of a constant is just a constant. And this is mu xy This will cancel this, and you have minus mu x, mu y. And this is this. Later on, we will see how we normalize the covariance to make it a correlation that we are more familiar with. Next is doing this example. A mobile computer is moving in the region A, bounded by the x-axis. So let's draw the x-axis here, the y-axis. So it's bounded by the x-axis, the line x equal 1. So that's the line x equal 1. And the line y equal x. And that's the line y equal x. So the person who's using this mobile computer is moving in this block or triangular location of the city. And you can think of this as like 1 mile. So the person could be here or here or here or here or here. And we want to know if there is a relationship between the movement of the mobile computer. If he moved east, does that mean he moved also north more often? Or it doesn't matter. He could be moving east or west, and the movement north and south has nothing to do with the motion east and west. Now, by looking at the joint probability density function, it has the highest value when x is 1 and y is 1. It seems the person spends most of the time in this region. That's when x is 1 and y is 1. Now they are asking find the covariance between x and y. So covariance between x and y equal mu xy minus mu x mu y. And the mean of xy equal double integral of xy f of xy dy dx. Okay, so this is xy, and the joint probability density function is 8xy dy dx. Now we have to be very careful in choosing the limit of the integration. Dx is no problem. It just moves from 0 to 1. So that's dx, 0 to 1. Now why it doesn't go from 0 to 1? Because the person only moves in this region. Here, let me draw it. The person moves in this region. So it depends on where is he in x, that's how much he moves in y. So that's x1, that's y1. If he is here, x2, then that's the maximum he can be in y2. So when the person in this position, x2, he could be here, he could be here, he could be here, but he cannot be here because that's outside the region. He is bounded by this triangle. So then y, it goes from 0 here to wherever that position, either here or here or here. And that position will depend on x. So if he's in x1, then y will be the maximum he can be in y1. If this is x2, then the maximum y can be is y2 here. So that integral should be not to 1 but to y, which is x. Depend on the position. For example, if x here is half, then y will be from 0 to half. If x is 0.8, then the person could be in any place here from 0 to that position. Then we integrate. So this would be from 0 to 1. 0 x, 8 can come outside here. And this is x squared, y squared, dy dx. So this will be 8, 0 to 1. X squared is just a constant, it has nothing to do with y. And the integral of y squared is y cubed over 3 dx, evaluated from 0 to x. And this is 8 over 3, 0 to 1. If you plug for y, x, that will be x squared, x cubed. And then you plug for x for y0 minus 0 dx. And further, this will be 8 over 3, 0 to 1, x to the power of 5 dx, and this will be 8 over 3 x 6 over 6, and evaluated from 0 to 1. And this will be 8 over 18, or it's just 4 over 9. Okay, so we found this part. Now we need to find mu x and mu y. Well, mu x equal x f of x dx from x0 to 1. That means I need to find f of x first. And how do we find f of x? Well, f of x equal f of x y dy for all values of y. This will be integration 8x of y dy. Again, same analogy we said. If this is x and the region is here and this is y equal x, then dy, all possible values of y, it's from 0 to here or here or here, depend on the value of x. So that will be from 0 to x, and this will be 8xy squared over 2 evaluated from 0 to x, and this will be 8x squared minus 0 divided by 2. So that is 4x cubed. Make sure you indicate for x larger than 0 and less than 1. And we can do the same thing for f of y. It will be 8xy dx. And let's plot here, just we follow what are the possible value for x. Okay, to determine the limit for the variable x, it's a little bit tricky. If I want to find fy for a specific value of y, let's say here, then that means I have to integrate. Imagine f of xy is a surface area on top of this triangle. Then you have a knife and you cut it and you integrate the area of the surface along this path. So you will integrate from this point x1 to 1. But what is x1? Well, from this relationship, x1 equal y1, x2 equal y2. So if x is a variable keep changing, then the limit here is constrained by y. If I want to find y2 here, then the integral should be along this line. So it will be from this x2 to 1, and x2 equal y. So this will be from y to 1. And when you integrate this, it will be 8x squared y over 2 from y to 1. This is 1 squared minus y squared times y. And this is 4y 1 minus y squared. And we specify for y larger than 0 and less than 1. So we found the marginal density function for the random variable x and y. So now we can find mu x. Mu x equal x f of x dx. So that is x, and f of x we found it to be 4x cubed dx, and x from 0 to 1. And this is 4 over 5x to the power of 5, 0 to 1. So that's 4 over 5. And the same thing if we find the mean of y, that would be y, f of y, and f of y is this one, 4y 1 minus y squared dy from 0 to 1. And if you do this calculation properly, mu y will come 8 over 15. So the covariance now is 4 over 9 minus 5 over 4 times 8 over 15, and this equal 0.0178. So the covariance is very small. So there is no relationship between x and y. There is no relationship between the motion of the person east and west or south and north. When you calculate the covariance, it could be a large number as 40, 30, 20, and when you try to compare two processors to see how X and Y are related to each other, there is a lot of strong relationship between them when you are using processor 1 or processor 2. If you use the covariance, it will depend on the input of X and Y. If the values of X and Y are high, then the covariance will tend to be large. So you may have covariance of X and Y as large as 40. Then another processor, the values of X and Y are smaller and the covariance may be 20. So you may think, oh, the first processor, the covariance 40. The second is 20. So the first processor has a process X and Y and there is a strong relationship between them. No, because X and Y started with a larger value. So here we have to normalize the covariance. So I can compare two systems or two variables regardless of their values. If their values are high or low, all I care is there a relationship between them. So if I normalize the covariance, then I will get the correlation. And the correlation is this. It's the covariance divided by sigma X, sigma Y, the standard deviation of X and the standard deviation of Y. And when we normalize it, then the correlation coefficient will always be between -1 and 1. For 1, that means there is a strong relationship between X and Y, and it is a linear relationship. When X go up, Y will go up. When you have the correlation coefficient -1, mean there is a strong relationship between X and Y, but it's inverse relationship. That means when X go high, Y will go low. And if we try to calculate the correlation coefficient for the same mobile computer example, then it will be the covariance of X, Y divided by sigma X, sigma Y. And the covariance, we already found it. It's this one, 0.0178. Now we need to find sigma X, sigma Y. And if we find the variance of X, it is X squared of XX dx minus mu X squared. And this is X goes from 0 to 1, X squared. And we already found f of X here. 4x cubed minus mu x, and we found mu x here. So that is minus 4 over 5 squared, and this is x6 over 6 times 4 from 0 to 1 minus 16 over 25. And this is 2 over 3, 1 minus 0, 1 to the power of 6, 0.64. And if you calculate this, that will be 0.03. Then if we find the standard deviation of x, it's the square root of 0.03, and this will be 0.173. And if we find the variance of y, it will be y squared f of y dy minus mu y squared. And this is from 0 to 1, and we found f of y to be y squared 4y 1 minus y squared minus mu y squared, and we found that to be 8 over 13 squared. And if you carry out the integration, you should get 0.049. And the standard deviation of y will be 0.221. So the correlation then will be the covariance, which is 0.0178 divided by the standard deviation of x, 0.173, times the standard deviation of y, 0.221, and the result is the following, 0.465. So it's around half. There is some correlation, but not very, very strong. 0, no correlation. 0.5, there is positive correlation. So when the person is going east, it seems he's also going north. This is a summary. If the covariance or the correlation coefficient is 0, meaning there is no relationship between x and y, and we say they are uncorrelated.
If x and y are independent, then x and y are uncorrelated. We have to be a little bit careful. If it is mathematically possible for x and y to be uncorrelated without being independent. So you calculate the correlation coefficient 0, but that doesn't mean they are independent. But if they are independent, then definitely they are uncorrelated. Okay, that ends the last video in chapter 2. Thank you.